All right, guys, this is going to be the start of a tricky topic for us. Okay, it's exponential growth and decay. All right, today's part of the topic shouldn't be too challenging, but we need to understand the beginning parts in order to get a grip of the more challenging parts later. Right, exponential growth and decay. You would have actually seen this in action in its simplistic terms when you looked at compound interest, because that increases exponentially, compound interest, and as does geometric sequences, they increase or decrease exponentially. Okay, so you've, particularly with compound interest, you've really seen that to some detail. Geometric sequences we're going to do quite a bit more of today, and that will link all into how exponential growth and decay will work for us. Okay, so geometric sequence is what I want to concentrate on right now. Geometric sequences. Okay, the fact is, the main property is that the ratio is consistent. Now, what I mean by that is that the number we're multiplying by each time is consistent. And that's with geometric sequences. So the main property is the ratio is consistent. So if we look here, the ratio between 2 and 6, so basically what number we multiply by each time, is going to be the same as it is from 6 to 18, 18 to 54. So you can see here, you multiply by 3, multiply by 3, multiply by 3. So therefore 3 is the common ratio in that situation. This one here, 200, 100, 50, 25. Remember, I know a lot of you might think, oh, you divide by 2, but because we're multiplying here, we've got to think what we're multiplying by. So to get from 200 to 100, we multiply by 0.5. 100 to 50 times by 0.5, 50 to 25 times by 0.5. And actually, as a reference in the first minute of this, compound interest also works with this. So if we increase 100 by 5% each year, using compound interest, we do 100 times 1.05 to get 105. Then we technically then do 105 times 1.05 to get 110.25. 110.25 times by 1.05 equals 115.7625, etc., etc., times by 1.05 equals 121.5562. Right, what I'm showing here is that there is a geometric sequence in itself. And the common ratio of that is 1.05, because to get from one to the other, you multiply by 1.05. So compound interest and geometric sequences have the exact same property to them. And that all links beautifully to exponential growth and decay. But we'll come to that again in a second. So let's look at more geometric sequences. Oh, no, that's missing a page. Let's go to here. Right. Let's start with this. So 2 times 3 to the power of n. Now this is a geometric sequence. It looks different to a quadratic, it looks different to a linear, so therefore we know we're good. Generate the first 4 terms of the sequence. Right, it works in the exact same way as you would do if you want to generate the first 4 terms of a linear sequence. We want to work out when n equals 1, so the first term, what does that mean about the answer to that? So when n equals 1, it will be 2 times 3 to the power of 1. 2 times 3 to the power of 1 is just 2 times 3, so that equals 6. When n equals 2, it will be 2 times 3 to the power of 2, in place of n. 2 times 9, which is 18. n equals 3 would be 2 times 3 to the power of 3, 2 times 27, 54. And last one, the fourth term, 2 times 3 to the power of 4 is 162. So therefore the sequence is 6, 18, 54, 162. So that would be us generating the first 4 terms of the geometric sequence here. Okay, so that's relatively straightforward for us. Now, let's have a look at this one here. Now we want to find the nth term. Now again, this is a different method different method to how you do it for linear and how you do it for quadratic, which I know you've seen before. So, first step, we know, simply just based, if we look on this side here, that it's going to be in the form a times b to the power of n. It's going to be in that form there. This is what we want, because that's the form of a geometric sequence. Now, A we'll deal with after. B is what we want to concentrate on first. B is represented by the common ratio. So we have to look and say, well, what do we times by each time to get to the next number? So 10 times 5 is 50. 50 times 5 is 250. 250 times 5 is 1,250. So therefore, we know the common ratio is timesing by 5. So therefore, B must equal 5. So we've got A times 5n. Now, in order to work out what A is, let's look at the first term. Now, when we're looking at the first term, n must equal 1. So n equals 1 if we're looking at the first term. So it'll be A times 5 to the power of 1 equals, now we know what the first term is because it's given to us here. So the first term is 10. So A times 5 to the power of 1, the first term, equals 10. So now we just work backwards and say, well, something times 5 equals 10, which is 2. So 2 times 5 to the power of 1 equals 10. So therefore, A must equal 2. So my final answer, if I want it in this form here, is 2 times 5 to the power of n. And that's how you find the nth term. If you need to relook at this video, this part of the video, please do. Okay, before I end the video, I want to show you the last step of what we want to do here. So, I want you to use everything we've just spoken about there and think about this question. What would a graph look like if we were to plot y equals 2 to the power of x? Okay, firstly, that's an exponential graph. And similar to the geometric sequence, hopefully you've got an idea of what it might go up in, how it might look if it went up in that amount. Okay, so let's now have a look at what this might be. I have put a table of values just like I would do if it was a linear graph. Okay, just like I would do if it was a linear graph. So I substitute negative 2 in the place of x. So 2 to the power of negative 2 is 0.25. 2 to the power of negative 1 is 0.5. 2 to the power of 0 is 1. We should all know that. In fact, we should all know these two as well, to be honest. 2 to the power of 1 is 2, and 2 to the power of 2 is 4. So now we've got enough information for us to be able to draw this out. So let's have a go at this. 0 minus 1 minus 2, 1, 2. Okay, negative 2 to 0.5. So obviously we'll label that as x, label that as y. Let's label this as 1, 2, 3, just so we've got some context over the size of the graph. So negative 2, 0.25, so it's going to be around here. Negative 1, 0.5, it's going to be around here. 0, 1 is here. 1, 2 is here. And actually, maybe I should just go up a tiny bit more because 2, 4 is there. Now, as you can see, what we've got here is we've got an exponential graph because it's going to keep getting bigger and bigger. And if that continued, it would be up and up and up and up and up like that. And if this continued, it would be across, it wouldn't ever touch the x-axis in this case, but it would be like that. And that's an exponential graph. Okay? So what we've looked at today, in today's video, is geometric sequence and how it's related to compound interest, and then how it brings an exponential. Geometric sequence in regards to generating terms, geometric sequence in regards to finding the nth term, and then finally how and why we draw exponential graphs like we do. All right, best of luck with today. It leads nicely on to tomorrow's difficult topic.